best way to get good at this is just to keep practicing. Practice, practice, practice. All right, so this one has the hexagon in it. You guys are going to be pros at this, drawing your perfectly shaped hexagons. So before I start here, how many total hydrogens are in this compound? Total hydrogens. Still haven't heard the correct answer. Huh? 10? I really don't random numbers now. Better question. Do all the carbons here have the same number of hydrogens or different amounts? They actually all have the same number of hydrogens on them. Yep, they all have one hydrogen. All right, so the thing here is that the ones that have a zero formal charge, the fourth one is implied. And just for this first drawing, I'm going to draw them all in so we make sure that we're clear about what's going on. So if you're ever unsure, I highly recommend when you first start these to go ahead and just draw them in, at least for the first structure. And that way, if you ever forget how many H's there are, or you're thinking you're violating an octet rule or whatever, you can always come back and look at that first structure. So in order for a carbon to have a +1 charge, it's implied to have the 1 bond to H, right? If it had 2 bonds to H, it would have had a 0 formal charge. So we can't go with that. So here we go. What is a good starting point for this example? Yep, if you see a double bond O, you see that carbon-O-carbon, that's always a good place to start. So we're going to go ahead and bump this up. And let's go ahead and draw the result of that. Okay, this is not working out. Let me raise this a little bit and then zoom in on the software itself. I keep bumping the camera with my pencil. Come on, zoom in. There we go. A little bit better. Yeah, I have room to write now, yay. All right, so hexagon, and then single bond to O, and this now has a negative charge. So if it has a negative charge, how many lone pair electrons are implied?
3.
There are 3 pairs of electrons. Okay, and then I don't think this is going to work out right. Oh, that's why it's not. I actually have a negative charge on my paper here. This should be a negative. The same thing though, if you have a negative charge here, it's still going to have the same number of bonds, but the main difference is it's going to have a lone pair. Yep, so we have a lone pair there to work with. Sorry about that. I realized it's negative here. And the reason why I was able to recognize that mistake is because if I were to have done that with a plus charge there, I would have had 2 adjacent like charges, which doesn't happen. So that structure probably wouldn't even exist. Alrighty, so we have this structure now. Let me see if I can zoom in further. Oh, that's the extent of my zooming. All right. So next place, where can I go with this next? So move the double bond. Yep, so we can move the double bond. Like so. And I like to go with the general theme of chasing the positive. That way you'll effectively move those electrons around the ring. Or just around your structure in general. Right, and then for the sake of discussion now that we are fully aware that there are 3 pairs of electrons there, we don't have to keep drawing them in every time, but that is a time sink. So you want to try to avoid time sinks if you can. But if you're losing track of things by making shortcuts, then you're basically wasting your time because you're getting wrong answers. So you have to make that call. All right, next one here, chase the positive. Do that. Okay, then we can do this. Double bonds now here. Positive is here. Remember that when the carbon loses the electrons, it becomes positive. Double bond there and here. All this stuff didn't do anything yet. And then still have a lone pair with the negative. Okay, keep chasing that positive, so we can now do this. So here, like that. And I think I can do, I'm going to go ahead and do one more here. And something that you might not have expected, but after you do the resonance here, does that ring look like something to you? It's a benzene, isn't it? Yep, that is a benzene ring. So you could show the standard all three moving at once resonance structure, where you flip the orientation of the double bonds. Yep, there you go. And this is actually the phenoxide ion. I'll give you the name for it here. Oops. Yeah, so we talked about phenol today a little bit. This is actually the conjugate base of phenol. We call them phenoxide instead, and it has this weird resonance structure stuff. There's probably maybe one or two more, but this is probably good enough here. So if I didn't do all this resonance here, looking at that one, you probably would, if someone were to ask if that's aromatic or not, you probably would initially say no, because you don't have the full ring structure there. But after the resonance for it, hey, that is aromatic. So this is aromatic. So I wouldn't expect you guys to be able to figure that out just by looking at the structure here, but my point is I want you guys to practice your resonance. It's important. Okay. Next example. Let's go ahead and take a look at that one. But before we do that, did anybody have any questions about this one? Good? All right. So next one. Oxygen. Got some double bond, double bond. All right. What kind of functional groups do they have in there? Yep, ester. And then what else? That's an alkene. Is that cis or trans? Trans. The two groups are going away from each other. Yep, it's trans. All right, so best place to start is the double bond. So you guys are going to love when you have resonance problems. They have double bond O because that's always a clear part to start. Okay. Here you go. Here we have a positive charge. I've seen other people when they teach resonance structures, there's usually a specific mention of heteroatoms next to positive charges, which is kind of like what we're having going on here. And that does lead to, that almost always leads to a resonance structure because of the fact that that lone pair can do something. And typically if you have a heteroatom, you're going to have lone pairs involved. So like your oxygen, your nitrogens, your sulfurs, things like that are going to have lone pairs to work with. So once again, a heteroatom next to a positive charge is going to be a resonance structure. So do that. Okay, so there we go. Double bond is now here. Okay, how many lone pairs does this oxygen have now? Has one lone pair. And then what is the charge now? Positive 1. So you could think about this similar to the carbon example we had earlier where I said if it loses electrons, it becomes positive. So we're actually showing that oxygen giving us lone pair to share it with something else. So initially it was hogging it all to itself. Now it's kind of sharing with its neighbor. So it effectively is kind of losing electrons. The same kind of logic. It becomes positive now. Okay. Where do you guys think we should go from here? Any ideas? Have it go towards the left? Yep. So If you're unsure, like from here, basically what we're going to do is if from this structure, and if instead this double bond moved over instead, is what I'm going to do down here. And that's the other option that you have. So we're going to move this down. So basically we're imagining this structure here, that double bond would be here. The thing is, though, that we have to do something else. We have to undo this one because that'll violate the octet rule. So we're going to undo that. So effectively, we are just moving this double bond over. And I think we're done now with this. So double bond here. Oops. That's the O minus. And another carbon, right? Okay. Where does my positive charge go? Should have a positive, right? Yep, so the one that used to have the alkene to it, that one is now electron poor. It's missing electrons, so it's now positive. This pencil. It's like it's devouring my lead. Just bought it too. It's like the first time I taught with it. Oh well. So positive charge. All right, I got one more resonance structure problem, and then we'll go ahead and start with the IR discussion today. I'm hoping you guys brought the worksheets that I asked you to bring. Okay, so this one is similar. Oh, interesting thing here, the two I just want to mention as an aside, is we're doing all this stuff with carbonyls. I'm showing you all the stuff that C double bond O can do. We actually spend about 6 weeks or so in OChem 2 talking about nothing but C double bond O. Like it does a ton of chemistry, so it'll be fun. And usually the first thing that we talk about with reactivity is the good starting point for resonance is this. This actually explains a lot of the reactivity. Is the fact that carbon ends up being positive in a lot of cases. All right, so O minus plus, oop, there's double bond, triple bond. Okay. Okay, and just like the previous example here, so going back to the second here, we kind of have a similar setup as the second resonance structure, where we have the positive charge here and that double bond that's like 1 carbon away. So we can do a similar arrow push, like so. Okay, double bond, O minus. The carbon that used to be double bonded, it no longer is, so it's positive. And then we have C123N. Okay. I think now we need to start playing around with this part of the molecule with the C triple bond N. So we have a situation here that's actually really similar to what we had over here, where we have the carbon with multiple bonds to a heteroatom. So if I were to move that triple bond, one of the pi bonds in there, which direction does it go? Do they go to carbon? Do they go to nitrogen? The arrow. And why is that? Or electronegative. Yeah, so the more electronegative it is, it's going to go that way. So the thing is that if you look at all the heteroatoms we're going to deal with, they're all to the right of carbon. So they're all more electronegative. So the arrow push is going to be the same regardless of what your heteroatom is. So if it's oxygen, nitrogen, whatever, it's going to go towards that heteroatom. If you have if you're moving pi bonds here, so do that. And then what that's going to do for us is it's going to give us a positive on the carbon, and then we now have a positive to chase. Does that make sense? So you basically want to think about where can we start, and that's usually the hard part is figuring out where to start. And then you can kind of just go from there. All right, so let's draw the result of that. So this is double bonded to N. This carbon here is now positive. And this nitrogen over here has 2 lone pair electrons, negative. And then this part of the molecule didn't do anything. I could technically do that again. So you might initially think, oh, this C double bond N has 2 lone pairs. You could probably do what's happening with oxygen. It's like with oxygen, we do that all the time, right? But it's not okay here. And the question I have is, why is it not okay? So doing this arrow here to here, why is that not okay? Yeah, you're going to get a -2 on nitrogen, a +2 on carbon. You have a high energy resonance structure. That is not a valid structure. So we're going to avoid that entirely. Any other ideas of what I can do here? Yeah, we can move the double bond here down. So we can go ahead and do this. Do I have to move this double bond? No, we don't. Because carbon does not have an octet here, so it is fine. So we go ahead and draw the result of this. So double bond, and I'm not doing proper bond angles here. And I'm actually really fine with that with resonance just because it helps you keep track of everything. But I guess technically the geometry would be changing too. All right. And then positive. Okay. And I think we have about all the ones that I'm really worried about. So what do you guys think? Which one of the 5 resonance structures is the major contributor? Which is the dominant form that this compound would take? The first one. So the reason why, so if you're ever asked which resonance structure is the major one, it's the one that has the most bonds to it, has the most bonds in it. It's also one that has the largest or the least amount of non-zero formal charges. So if you're able to get a structure that has no non-zeros, you often end up with a case where you have the largest number of bonds as well. So here we have the maximum number of pi bonds. Here we're like 1 less than this one and all the other ones, I think. Yeah, so this one has 1, 2, 3. This one has 4 pi bonds. Okay. Go ahead and